Okay, so let's start. I know that so the one that are not involved in getting credential, they can give me attention, so we can start. Thank you. Okay, so let's start with the theory. So we are going to use 3 theory concepts today. So we are going to evolve a little bit on what provide additional details on what Filippo told you today about RISC-V architectures. We are going to discuss bandwidth and flops that you already have been touching this morning. We are going a little bit more in detail, and we are going to use the roofline model. So how many of you know already the roofline model? Okay, so not many. So I'm coming from University of Bologna. Bologna is a beautiful city. We are proud inventing of really good inventions. So tortellini and lasagna bolognese. So a lot of calories, but also many computational calories. So in Bologna City nowadays there is the Human Technopole, which hosts the Leonardo supercomputer. It also hosts the SNWF weather forecasting supercomputer, and it also hosts the CERN Tier 1 system from the CERN grid, so from my NFN department, and also it hosts the small Montecimone that you will play today. And so we really care about computational calories, mostly when it's hot in summer, because I need to start the air conditioning at home for all the heat that is produced nearby the city center. So part of my research that I'm playing with is with the energy efficiency of computing system, but today we are going more to see what is a supercomputer. First question for all of you. So what is a supercomputer? Is this guy a supercomputer? No? Is this guy a supercomputer? So why this guy is not a supercomputer then? Can someone of you tell me why? So you mean it's just because it is a single node? So if I had to put 2 in the slides here, no, so let's say that there are 2 of these connected. So is it would it be a supercomputer? So a guess is that a supercomputer, it should have enough performance, computational power. So what do you think? Do you agree with your colleagues? Given the current technology, so in the moment, in 60s, that would have been a supercomputer. That's a good point. Then, so how you define the computational power? Memory operation, number of floating points per second. When you say memory operation, what do you intend? What do you mean? Load and store. Load and store memory bandwidth. Who knows the difference? So memory bandwidth, floating point operation, number of load and store. So how many load and store per second can do this machine? 2 billion. Who offer more? 2 billion 1, 2 billion 2, 2 billion 3. So we don't know it yet. In a couple of slides, we will look at it. So by definition, a supercomputer is indeed what you told me. So a supercomputer, it is a one of the above the 500 most powerful machines in the world in that period, and powerful in terms of its capability of doing double precision floating point operation per second. And it is important, the double precision floating point per second, because you see many slides in these days about performance and flops, and sometimes they go till the 4-bit floating point per second. So if you take now, let's say, latest announced Broadwell, the latest announced GPU from NVIDIA, they announced that, for instance, for doing large language models, the new RTX computational unit, which is a fusion between the ray tracer unit and an inference engine for transformers. It does operation at 4-bit floating point number representation, which if you think about 4-bit floating point, it basically goes from minus 0.5 to plus 0.5. And so you have many 4-bit floating points inside a 64-bit floating point registry. You have many, no? So that is still a floating point operation, but they're not double precision. The reason why supercomputer, it is a machine that stays, let's say in 2024, between this range of performance between the blue point and the orangish point. The orangish point, it is the fastest one, so the number 1 in the list, and the blue one is the 500, the last one in the list of 500. And you, in a moment in time, you had this machine that was capable of being in the list, you can name it supercomputer. All the others are out. So that is indeed double precision floating point counting in a specific moment in time. But then another thing that we were saying before is that, do you need to have connectivity? Do you need to have 2 nodes? So before, when we were looking at a small Intel machine, it was a single node, and you told me it has to be 2. There is the need of having interconnect. The need of having interconnect is just because you cannot be in this range of performance with just one system. If you could be with 1 core, you will be the happiest person in your life. No? Unfortunately, you cannot. So that's why then you want to have faster, low latency network and all these components. But this is just a by result of the fact that you want to be between. Today, this goes around from tens of petaflops to exaflops. So you go to be in the list, to be one of the members of the supercomputer today, you need to have a range of performance which goes from 10 petaflop per second double precision to around 1 exaflop, so 10 at the power of 18 floating point operation per second. Just for you, we open and close a bracket. Today, you are around, if you look at small precision format numbers used for AI, you could also reach the 1 petaflop with just 1 card and 1 node. But this is a tensor operation with reduced format, numerical format. We are here looking at 64-bit because engineer, mostly physicians, people from hard sciences, and they do like to be sure on the number that they put on the table. Okay. And stability of all the numerical methods, of course. Now, the question is then, we can go a little bit inside the 2 systems that we were looking before. So if we extract just 1 single node and we look inside, we want to see the difference, no? So this is 1 motherboard of the CPU part of the Leonardo system, a picture. So if you open the node, you will find 3 of these, and this is one of the motherboard that you find inside one of the computing nodes. This instead is the motherboard that with all the components that you had in the small machine. So in order to have high performance, that is what we have to put inside the supercomputing machine, because we want to build a system which can do exaflop of performance or 100 of petaflops of performance. You need to make something that are different. So who sees the first difference? Multiple sockets. So here you have 2 sockets. Here you have only 1, which is underneath and you don't see it. And probably, if you would look at it, the size of the socket is larger in the supercomputing node, you see. Second difference, lot of RAM modules. So you see here we have 4, 8, 16 RAM modules, spots, place to put the RAM modules. And indeed, and here you have only 2, you see? Only 2 DRAM modules. And The reason why you put 2 sockets in the compute node is because you want to have many DRAM modules. Because the problem is that if you take only one, you have limited space, limited pin pads to connect DRAM modules, MPC Express connector. Because other things that you want here is that also you need to have PCI Express connectors because you want to have the network. So the InfiniBand network is a PCI Express device. So you need to have this pin. And all the remaining one, we will see, are used to transfer power inside that socket. So there is a contention today in today's compute node design between how much power I can put inside, how many pads I use to provide power inside the node, and how many pads I have left for connecting DRAM and to connect the PCI Express devices. We are limited by this story. And so this is the DRAM modules. Then what other differences that you see here between these two pictures? There is no storage. There is no storage. There is more one probably within here, but not storage, because you don't really, you are going to use parallel file systems for having storage, so remote storage. You need to have something, otherwise the operating system won't boot. And you need to have scratch disks, which are maybe local and faster. Then, so no storage. Other differences that is what? Cooling. So power, indeed. So there is, here we have a rotating fan for cooling it, the processor. Here we don't have moving fans. We don't have heat sinks and everything, because this board here has been engineered to be directly liquid cooled. So this is a board manufactured by Atos, but other vendors has it. So which supposed to have a copper layer which directly touch everything, on which through it will pass the water to remove heat. And as a side of the heat, so let's imagine to remove all the components that we just described from this motherboard. So let's remove the sockets, this square here. Let's remove the DRAM. Let's remove some minor controllers. There's still many space left inside that motherboard. Who is brave to guess why there is of you who is brave to guess why there is so much space there left? Almost, but not exactly. Someone else has some guesses? Yes? GPUs here, this is without GPU module. So there are some smaller components here. You see this list here of small components here, that small component there. And so this one, for instance, are all inductors, which are used by the voltage regulators, which has to convert the power, which is entering somewhere here. You see these two copper connector are probably the points where 48 volt or 12 volt DC power is entering in. So this is a major difference. So this one you power with probably with the USB-C type of connector. USB-C could probably provide it 30 amp, 5 volt, which is not bad today for today mobile phone, but I mean the past it's going to be 20 watt or 60 watt types of TDP. This one here we are around, we need to supply, if this would have been a GPU node, around 2 kilowatt of power. 2 kilowatt of power at 12 DC, or at 12 DC, how many ampere are? 12 volt DC. You are in the range of multiple, yes? No, you can tell it. Okay. So if this consumes 2 kilowatt of power, let's suppose you have 3 GPUs, 300 watt each. You are, for GPU 300 watt, you are on the range of already at 1200 watt. And then you have other components, CPU 180, 200 watt, you are already 1600 watt. 1600 watt, then something else. You reach easily the 2000 watts, and you power usually. So you tend in a rack to have to centralize the converter, the power converter from AC to DC, and you have copper, so-called bus bar, so copper bus bar which pass through all the rack, and you have physical connector here at 12 or 48 volt DC. So let's suppose it is 12 volt DC. You are consuming 2 kilowatt of power. How many amps are entering here? 100 and something, yes, 200, yes, 100, 170, yes, between 100 and 200 amperes. So this is that here, so that's why you have really wide metal layers, and this is why the board is wide, because you have power which is entering, and there's a lot of current, so which enters. And you need to think that another number that somehow is scary if you don't think about it is that one of these sockets that may consume around 180 watt, at which one is the voltage level at which you power one of these sockets? 1 volt. So 180 watt, 1 volt. How many ampere? 180 ampere. So that's why you have a lot, all the pads, all the pins, most of the pins just you are kind of putting 180 ampere in wires which are thick as an hair, so that you need to have many. Okay, that's why you need all this area just for providing power, current. If now we think about a GPU, an H200, so the last announced one, which consumes around 600 watt one. Okay, we start to have fun, no, in terms of providing current there. So that's when you think about it, when someone is telling you that today processors are power cap, they're actually current cap, in a sense that is the current that enters the chip that is limiting. So you cannot really provide more than 100 ampere into the chip. So you have some vendor which has technologies which can have voltage regulators that are inside the package, so you can increase the voltage, you decrease the amp, so you can then provide more current. Or here, as here, in the board you enter at 12 volt, and then you need to have many voltage regulators, many, because they have to convert the 12 volt to 1 volt to feed it into your socket. So all this area here is just power handling that has to be power delivery. This is not the 4 things that makes the difference. There is finally another difference. Who can spot it? There is another difference between these two systems. And this is this small controller here, I think. No, this one. This one. This one. This one. This one is you can't see it, is named as A-Speed. This one is the BMC, board management controller. So if you are a system administrator of a system, you want to connect even if the node is, even the operating system is broken. So you want to have an Ethernet connection to your node, which bypasses everything that is so-called out of band. So it doesn't pass from the operating system, but it goes out of band. And you have it here. Here you don't have it because you don't want someone to remotely connect without you to know in your machine, in your laptop. Okay. So this is another difference. So if we go fast and recall the home, so we have the processor, which is different. So now let's go in deep to check the differences, no? So let's look at the processor. So these are so you have the slides into the folder of the today lesson. So if you have trouble in seeing, you have it there. So now, so these are the two processors. So if we look at the spec of the two processors, these are the two differences. So this was the processor in the small computer, $300 for the processor, and this is the other processor that we have two, almost 10K for one socket. Okay, so 20K of processor in that computer node. We hope it deserves it, at least 10K. So let's see where are the differences. So first difference is this was the one that I took. It was a relatively, let's say, new processor which had, if we look at, so the first difference are number of cores, 10 cores here, 52 cores here. Okay. Then of these 10 cores, so let's let's see where so we said this should be more performing than this one, no? At least this costs a lot more than this one. It should be better, no? At least, no? That is what we hope so. So who can tell me why this the processor in Leonardo is better than this one? So core I already spoiled. Can you see other differences? I mean, if you pay 10K, what more than the other? What we would wish to have it? More cache. More cache, yes. So 100 megabyte of cache against here is not 12 megabytes. So a factor of 10 in the cache, which almost justifies a factor of 10 in the price. No, is more a factor of 30 in the price. So it cannot be just the cache. Some other things, reliability. Yes, it is not here, but it's likely it is in. I have in the next slide. We will take it about the reliability. Other differences, connectivity. UBI. So connectivity, I guess what we said before is that is true. What will be connectivity in the world of supercomputer will be the generation of the PCI Express lane, number of lanes, and which allows you to connect more accelerator, more network cards, and the bandwidth at which you talk. So it's likely this to have it more, but I didn't report it here. Other differences that are in this slide or that you wish to have. Frequency. That is fancy, because here you see this is actually slower in frequency than this one. So this runs at turbo frequency. So the base frequency is 2.1 gigahertz. The base frequency of this guy, it's around 330, I think. I think it's not even reported, the one which is the default one, but it's so let's say even turbo, here you are at 440, there you are at 380. So frequency is not the faster. This is already controversial, no? I mean, I paid more, I wish to have a faster score, but it's not. Yes? What? The processor is more efficient? So you mean technology node. Technology node, they are both Intel 7. So they have the same technology. Scalable, 52 cores against 10. Yes? Thread to core ratio, so here you have hyperthreading, here you don't have it. So, but in HPC, you tend to switch off the hyperthreading. It's not cloud, so don't really use. Yes? So internal architecture, that's a good point. So if we look here of this 10 node, I mean, from 10 to 50 is a factor of 5. So it doesn't display in the factor of 30 in cost, no? But if we look at it, we see that here you have performance core and efficient core. So out of the 10, there are 2 which are named performance and 8 which are named efficient. So it is likely that the microarchitecture of the efficient core, it has a shorter pipeline, so number of stages, maybe less out of order capable, so maybe smaller caches. So the microarchitecture is different of the cores. And that's also why this one may run faster in terms of frequency, and this one runs shorter, is a higher, lower frequency. To be true, the other difference that you don't see here is that it's consumed 350 watt, and this is around probably 12 watt. So the difference between the frequency, why this one is lower, is probably because it has many cores, it consumes more. You cannot clock it at 4.4 without breaking the 100 ampere that you need to feed into the socket. Okay. So it's likely to be power capped in terms of the peak frequency. All the processors that we live today in our generation of compute system are power capped. So this ends of Denner scaling is where we live. No? Then so by looking at performance, so how much then Seeing it's a little bit controversial, so there's a question for you. Is there someone who can tell me how much faster in terms of some performance metric is this guy compared to this guy here? General, the entire socket. So the performance metric that we already said before, and we want to enter the top 500, so we care about double precision floating point per second. So how many double precision floating point operation per second does this one compared to this one? How many more? So someone of you knows how to do it? How much? At least 5 times more. So let's start with the computation. So we have also the black. So which one are the elements that we need to put in the equation for computing it? So number of cores, then frequency. Okay. Okay. What else? Instruction per clock cycle. So this is so first is I put it here. It's not exactly what, so number of instruction. Which instruction do we care? Use, multiply, add. So the flops doesn't specify which type of floating point operation we care. We know that now it's the tricky where we a little bit cheating is the fact that we know that when someone is going to measure it, it's going to do a matrix multiplication. So it's going to do multiply and add. So that's why fuse, multiply, add are more interesting than, because there are two. I can count two for every instruction. So a little bit of cheating, but it is. So here is the number of floating point flop operation, double precision, per cycle. So how many floating point operation per cycle I can do? So here I have a pair, here I have a pair. And this is equal to my double precision flops. Okay. Then frequency. Which frequency should I put it there? Turbo or nominal frequency? I mean, let's vote. How many of you vote for putting the turbo frequency? 2. How many of you vote to put the nominal frequency? Okay. So you will be lower in the top 500 list because you will put. So since it is something that is also here a little bit controversial because when someone is computing the efficiency at which your architecture is running in flop, if you count your peak performance, so the nominal one with the nominal frequency, you multiply by 2.1, but when you measure, it runs at 3.8. So you may think, look, I have a impact which runs at a 99% of efficiency, but in reality, you wrong the denominator. So you need to put the one which you are supposing to run. And by Intel, this turbo frequency is guaranteed to run when you have 52 cores in a correct cooling and TDP. So here you should put turbo frequency. I mean, that's why you put the liquid cooling there, to avoid that. Then, how many, for these two processors, how many flop per cycle do we have? So let's do the computation. So this guy has 52 core. It runs at 3.8 gigahertz. And then we need to decide how many flop per cycles is capable of. So who can tell me how many flop per cycle this guy is capable? Let's wait 1 second to answer. So let's also put the number for this guy. So this guy has 10 core. So 10 core, but they are different. So one is the 2 performance core 8, they have different free turbo frequency. So this will be 2 time the frequency of the performance one goes at 4.4, and the plus time the number of flops per cycle. And then we have the other one, which are 8 plus 8 at the frequency of 3.3. And then we still miss these numbers for all of that. So here we see already that there is a factor of 5 that before was said, but we have additional number here to check. So these one are the missing information, that the information that you were missing. So the ISA that we saw before defines for Intel the capability in terms of SIMD capability of each processor. So if we go here, the core of 300 euro core, it supports Intel AVX2, so which are 500 and 256 bit wide. So this is capable of doing, and also have support for fuse multiply add is likely. So this one, so it has so this number for Intel for that machine there, it is 256 bits divided by 8, because you have 8 bytes within a double precision floating point number, and this give you a parallelism which is of a factor of let's see, sometime I get distracted. So if it was 2, it will be 128. It will 4 will be 6. So it is these are bytes. Yes, sorry, this is 64 because these are bits. Sorry, divided by 64, so you get the 8. That was you get the factor of 4. So these will be 4. Okay, floating point within the two. That was, yes. Yes, so here we have to multiply by 2 because we have the fuse multiply add. Okay. And 2 ports. 2 ports is dispatching, but the unit is just that unit. I mean, in the Skylake, if you get this other one, so this one, which is the VX512, and you have 2 units, then you have 2 units. But here you have only 1. Okay. So this is time, so which means that the number that we put here is 8. So 8 double precision floating point per cycle. Okay. So if you do the arithmetic, we do 2 times 4 times 4.4 plus 8 times 3.3 multiplied by 8, which goes in the range, if I don't recall wrong, of around 300 gigaflop per second. You know, see if it's correct. Says 10, no, yes, 10 times around that number, no? So let's look instead at this guy here. This guy here, it has AVX 512. So instead of 4 per cycle, since it's 512 bit, we get at 8. We have a time 8, no? Because it's wider than this one. And it has also fuse multiply add, so we get a time 2. And then we have 2 units of this kind. So we have got another time 2. Okay. So there we are at around, so this is 32. Okay. So 32 times 52 times 3.8, it goes around 6 teraflops. Okay. So it is faster. And you have 2 sockets. So this is faster. So it deserves the money that we pay if we need to do the matrix multiplications, okay, double precision. Then is the only difference that we have. So we said before memory. So let's look it from the perspective of the DRAM memory. So memory specifications. So now it gets a little bit more tricky to do the arithmetic, no? So this processor here, so can you tell me how much how much better is the memory subsystem of this 10K processor against the 300 euro processor by looking at these numbers? Time 4. Okay, so first thing is memory channel. We have 8 memory channel against 2. So what is a memory channel in practical terms? Number of memory controller in the processor, which also is equal to the number of physical memory component that we can connect. 2 DIMM here, 8 DIMM here. So memory channel is how many slots we have to connect memory. Then so you have 8 memory channel against 2 here. Second one is that someone told me before reliability. So reliability is on this information here. Error code correction, yes. Error code correction, no. So if you get a cosmic ray which hits your DRAM, which happens, I mean, when you are in the unlucky moment, this one will tolerate it. Here, you will flip the bit. And you will eventually never know, or you will get a kernel time. Then, the other thing that is different, it is, so now, so what is the difference then so the difference of having more memory channel, it means 2 things, no? It means that we can connect more memory component, so we can go from 60 gigabyte of maximum memory space to 4 terabytes of memory to each of the connected to the socket. The other things which is different is another number here, which is not really different because they support the same type, but then still we don't know the bandwidth. To understand the bandwidth, we need to decipher this number here. So DDR5 for 4800 mega transfer per second. This is the capacity of the controller. So mega transfer per second, so is a DDR memory is double rate, so it means that it transfers data on the positive and negative edge of the clock. So here is transfer. If you look at the frequency of the memory controller, it will be the half, because you transfer data on the positive and negative edge. And then you need to understand how many bits you transfer in each of the flip. And that's 64 bit. I have a slide that we goes more in numbers there. So here we have now higher bandwidth. So if we compare it, these are 2 channels times 64 bit, so 8 byte times 4.8 giga transfer. So if you do the arithmetic, it's 216 times 4.8, so it is around 64 gigabyte per second, roughly, in the range of. Here you have instead 8, so you go a factor of 4 more, which goes then to the around 300 gigabyte per second of peak. So we are speaking about just the datasheet. We don't know if when we put together it will run it. This is just its capability from what you are paying for, I mean, on the paper. Okay. Then, as I was telling you, we have the power. So this is what we discussed already, all the conversions, all the space in the motherboard for handling the power delivery, which is different. And then we have all the different connectivities that you don't see. So the fact that you have all the different connection between the socket, and also the capability of connecting NVLink if you are going to be, if it is a processor which has paid the license for the NVLink, so ARM or the old PowerPC had it. or will be PCI Express of some gen for a given generation. So based on what we said now, and I'm going a little bit more into the arithmetic that we just did together. So what we have is that if now we look at the component, when we speak about performance, we see performance of two kinds. This is the first way in which we look at the processor. So gigaflop per second and bandwidth of the memory. This is the first two things that we pay the money for. Then we need to, so how do we compute it? We get a glimpse. I have a set of slides which does the arithmetic a little bit better, more precise. You can look it, I go fast. I will just stop in some points. And then we will look to a theoretical framework to now understand, is it, I mean, we knew already from the process that we saw before that there is a factor of around 100 in terms of the gigaflop between the two processors. And there is a factor of 4 in terms of memory bandwidth. Is it enough? Is it worth for me to pay around 30 times more money for that improvement? So that's a question that we need to ask ourselves. So if it's a desktop machine, maybe it's enough, maybe no. It depends on the application. So it depends on what we need to run on it. So we need also to understand, should I put more money in with having more memory channel? Should I put more money to have a higher peak performance? So how can we choose? So, I mean, who wants to have more flop? Raise the hand. Who wants to have more memory bandwidth? Raise the hand. You cannot have both. What do you take? Flops? It depends. You really cannot answer. You don't have, I mean, you need to know your application. You need to know where you are in a current moment in time, but where is your bottleneck for your application in a given moment? No? So how do we measure flop? Here is what we wrote here with the equation. So number of floating point units. These are actually the number of floating point units. This is what actually before Filippo was telling you, no? Inside its own long vector unit, it had 8 double precision floating point capabilities. So the number that you need to put here for Filippo machine, it's 8. Okay, it's the number of floating point unit that you have inside your machine for each core or for each computational unit, no? Yes, and also times 2. You have only one vector unit per core, one port. So, but you could put 2 if you wish. Yeah. Or you can just double the number of lane in this vector architecture. So the frequency is the nominal one. Yes, and this is why they're cheating. That is truly something that I can say you're cheating, because I had when I was a PhD, I had a lot of discussion with people in Cineca, with the program manager there, about saying yes, but we may save some power in the LIMPAC, and he said no. I mean, the efficiency is 99%. It's fully utilized. Then if you go to look the number, they were using the nominal frequency there, but they were running at the turbo. So they were running more faster than during the LIMPAC that what was nominal. So if you use the correct denominator there, you get maybe efficiency of a 70% or 80%. So there are communication in a large LIMPAC benchmark still. So then another processor, here I put also a GPU. So in a GPU, it's they tell you the peak performance. So it depends on the number of streaming multiprocessors, the parallelism and everything, but you can also compute it also there. So here is the equation that we went through before. So these are the factors. You can use it by reference. How do you measure it, the true performance then? So this is the nominal one. This is, I mean, I have a car which is capable in the speed meter says 200. I mean, it could go 200 probably kilometer per hour, but I'm not sure I will be capable of driving it at that speed, you know. So we want to measure the speed. Then the question is, how do we measure? So do we go in a long lane where I can really push it and go fast without having police? Shall I drive it in Germany, or to see how fast it can go? Or if I'm in Italy, I have a different path. So this comes to the benchmark. So the tool which I use to measure performance will change the number which I get. And in reality, this is true in a sense that, so if you, for instance, if you run it with the benchmark which has some limits because it's not capable or puts your performance, it puts you in a corner of the performance domain. So I mean, let's say another example, no? So I'm measuring double precision floating point operation per second. If I'm doing matrix multiplication, I'm using the fuse multiply add unit. If instead I'm just doing, I never do multiplication, I just do add the subtraction, I will not use the fuse multiply add. So I will measure a number of flop which is lower of a factor of 2. That is something that is depends on the code which I use to measure. The code which is used to measure the performance in the top 500 list is the LIMPAC or HPL benchmark, which solves a system of linear equations by using LU factorization. So this is the code. This is the problem that is used to solve. It uses, in order to solve the problem, it split the matrix's size in blocks. And according to the size of the block, you may fit better the caches, not fit the caches, have less or higher communication. So it's about you to tune your benchmark to get the highest number. You are really doing the race with the motorbike with your friends, and you want to go faster. So you're tuning it to get the fastest as you can. The other thing is that the LIMPAC, this problem, it's as you increase the number, the size of the matrix. So if you have higher memory, if you have a larger memory, you can put matrices which are larger. Then since the computation, the number of floating point operation increases at the cube of n, whereas the data increases at the factor that are needed at the square only, the more you make the matrix larger, the more it becomes computational CPU bound, and the more you can take advantage of the floating point operation of the floating point unit. The less you are limited by the boundary. That's why Dongarra won the Turing Award, and it is widely used to measure in the top 500 because you can tune it to really be only limited by the performance of your system, by the performance in terms of the floating point operation per second of your system, and not from the memory boundary. If you run the LIMPAC, you will run it in a second. You get a number which tells you, so you run the code, and then in the log of the code, in the log of the program that has been executed, it will report the number of floating point operation per second. So it measures a number of floating point operation, it divides by time, and give you the value. It also does some check on the correctness of the computation, the numerical precision. So if you are using floating point unit here, it's also, we open another big field. I mean, is the floating point unit standard? So the numerical error in doing the computation is the one of the IEEE standard, is another one. In case the floating point unit is not well designed or does some approximation to be faster, you will see it in the error of the computation. So this is about how do we measure the performance. How do we instead measure this? Which one is instead the theoretical speed limit in terms of bandwidth of the memory? So we already saw before that we saw DDR4 mega transfer per second. This table here put you some reference numbers between DDR4 and DDR5. What's the difference between DDR4 and DDR5, for instance? The difference is here. So we are speaking about DIMM, so DRAM blocks, the one that we can put in the channel slots. And the main difference between DDR4 and DDR5 is the fact that DDR5 can go at higher transfer rate than DDR4. So DDR4 as a standard, it can reach maximum the 3.2 gigatransfer per second, DDR5 up to 8.4 gigatransfer per second. Of course, depends of the memory module that you plug, its capability, no? Then the other thing is that you always need to be careful of the frequency. So the frequency is always the half of the transfer per second, because it's DRAM is dual rate transfer on the positive and negative edge of the clock signal. So at each clock period you transfer 2 times. That's why the mega transfer are the double of the frequency. So, and we'll see later that when you buy in Amazon a memory stick, they say frequency, but it's transfer. Okay, so you need to be careful on that. The other things that are different is the width of the data, the number of data that are transferred. So the DDR4 transfers 64-bit data. The DDR5 32-bit data, but it has double channel. So it transfers 2 of them. So it means that at the end of the day, you only transfer 64-bit for both of them. And then you have different telemetry and power consumption, but this is less relevant. So so when we buy a memory module from Amazon, you get this signature here. So this is the type of signature that you can find when you buy. The important information are these two here. So if it is so you have the size, so the capacity of the memory, 16 gig, and the number here is the mega transfer per second, the one that you need to multiply for 64 bits, and it gives you the bandwidth at which you can the bandwidth that you can transfer. So let's suppose we have a DDR4, this DDR4 memory here. So if we want to compute the bandwidth, we take the number of channels standard DDR4 is 1 times 3.2 giga transfer per second. This is number multiplied by 64 bit per transfer, and you get a number which is 25 gigabytes per second. This is how you compute the theoretical peak bandwidth that you can have on a system with that specific model of DRAM installed. So we saw before the specification of the processor. These were the maximum component that you could, the maximum speed that you can support, but at the end what you have is depends on the memory module that you install on the system. So for a DDR5 in that case, this is a typo, should be DDR5 here. You get same computation as the one before. So you get the giga, so bottom line, you get the giga transfer per second, so the mega transfer per second from here, 5.2 giga transfer multiplied by 64 bit, and you get the bandwidth. So this is DDR4, DDR5. Is that all? Not really. So we have another standard, it could be LPDDR. LPDDR with respect of the DRAM, it's different because it's soldered. So you solder it directly on something together with your processor. So here is one case. So in the Gray super chip, they use LPDDR. These are this block here. So this is memory soldered. It is, I have a slide later that compare all of them. It allows you to have more channels per chip. So that's why in a lot of AI accelerator, which you are dominated by the memory bandwidth, you are memory bound, you see a lot of usage in terms of LPDDR. LP stands for low power, so you can put it more and consume less power, because you are power limited. And also, for instance, this would be the processor, which has two LPDDR directly soldered into close to the processor. Same concept of the NVIDIA. Then is that all? We also have the high bandwidth memory, HBM. HBM, it's like DRAM, but they are stacked. So the image here on the top right, you see you have 4 DRAM chip die stacked on top of the memory of the controller. So this means that you can have higher bandwidth, because what you have is that you have a parallelism now. So If you look at the specification, so HBM2, it can support up to 3.2 gigatransfer per second. HBM3 up to 6.4 gigatransfer per second, so similar as the DRAM, you were in the same range, but you multiply these for 4-stack DDR die with 2-channel 128-bit each. If we make the computation, this becomes 1 kibibyte of transfer size. So each transfer, you transfer 1 kibibyte, 1024 bits. And that's why you get a huge bandwidth, because you multiply 3.2 giga time 1024. And then it goes to 3. Let's do the computation. So if we do it, these are bits, these are not, and you have, these are bits, these are not bytes, so you need to divide by 8 to get the byte. So if you, so which means that if you are running at 2 giga transfer per second, 1024 byte per transfer divided by 8 bit per byte, you get 256 gigabyte per second. If you, of these you have, for instance, 4, as in A64FX, you get 1 terabyte of bandwidth. If instead you have the version, if instead you have the HBM3, it goes at higher speed. If you take H100, it has 6 of the HBM memory block, so then you get a bandwidth, peak bandwidth, theoretical bandwidth, which is around, so one stack will be capable of transferring half a terabyte per second. You have 6, you reach the 3 terabyte per second. So the HBM give you higher bandwidth. When you compare all the 3 technology, what you have is that what you get is the following. So in theory, when it comes to power efficiency per transfer, per bandwidth, HBM and LPDDR are similar. However, the cost of HBM is much higher. So that's why you see that sometime, I mean, in the HPC system, you may have this one because you can pay more. In other accelerator system, you may get this one because it's slightly cheaper. It's 3 factor, it's cheaper. So how do you measure the bandwidth? So this is the theoretical one. We now want to measure it. We also have a benchmark for measure it. His name is Stream. What does Stream benchmark? It's a benchmark which reports you once you run it some bandwidth here information in running 4 different computational kernels, which are copy, scale, add, and triad. And what it does, it basically instantiates 2 vector, 3 vector, according to the kernel where you are measuring the performance. So copy does a copy of element-wise between 2 vectors. Scale does the copy, but it first multiplies for a constant, one of the vector, the source vector. The sum, it adds 2 vector elements and transfer it to a third vector. And the triad instead does a sum plus a multiplication for a constant. The reason why you do that is that because you have, by playing with these different kernels, an intrinsic different ratio between the byte that you transfer for each iterations and the computation that you need to do in each iteration. So these can inject more latency between the memory transfer between 2 subsequential load and store instructions, so you can saturate differently the pipeline. So, said that, what we are going to do now is to, what you are going to do is to connect to a machine to run these 2 benchmarks, so HPL and Stream, to measure the performance of a system. And the system where we are going to do, I will just skip some of these slides, are the Montecimone system. So the Montecimone system, it is a computational system, which is a small cluster that we have at the University of Bologna, which has been built, is based on RISC-V ISA. So it started as a project in 2021, where the only RISC-V processor, which was capable of running operating system and have a connectivity, a network connectivity, was a development board, which was the Sci-5 unmatched board. And so we have 8 compute nodes of this kind. Then no vector in 2021, because as Filippo told you, we were standing with the 0.71, and the V1, so the RISC-V vector 1 specification was just ratified in 2021. So no producer had time to implement in hardware this specification, because it was still under discussion. It has been just ratified at the end of 2021. That actually today you still cannot find an HPC processor class which has the V1 vector ISA, because it takes 3 years now to build, test, verify, do the mass production, and sell it, a component which has a new standard. So you can imagine that the latency between a standard is ratified to find it in the market, it goes with opportunity in terms of business, but it also takes time to design and to install and integrate something that works. So that was and this processor had in order RISC-V processor. So you will see peak performance not really so exciting. I mean, now we are in 2004, something has changed. 2024, what happened is that, I mean, there is a processor which is comes from China, which is built by the Sophon producer, which has 64 core. The previous one had only 4. These are out of order, and they do support RV071, because they started with some cores which had the old specification on that, which does not have support for the double precision floating point operation, so we cannot use the vector for measuring the performance. It gives some benefit, but not the huge benefit that we wished. There are other systems that have been also developed on RISC-V. It changed a lot. So there are now accelerators that you can buy in the market. So there are at least 3 vendors which I am aware of that they do accelerator based on RISC-V. So you have TensorRent, Accelera, Esperanto, which does AI accelerator. It shouldn't surprise that are targeting AI, because it's where investors are. And it is actually it is a different story if you want to build an HPC machine, or if you want to build an AI machine. An AI machine has wider market today, more venture capitals than an HPC machine, pure HPC. So that's also give different speeds to the development and benefits. The other thing, so the system that you will play today, it has also now these what we call the Montecimone V2 prototypes, which are the Milk-V, this processor which has the 64-core processor connected together, where you can also have better performance. And it's our more performing cores than the previous version, and we are working together with D4 for having a dual node, a dual socket system. We actually have already one in Bologna, but we haven't yet integrated in the Montecimone system. Now you see, it is the maximum between the number of bytes you need to execute your application divided by the peak bandwidth, the number of flops divided by the gigaflops per second. Then, if you do some operations which are you divide by the number of flops, then you do the inverse. What you obtain is that the flops over time, so flops per second, is the minimum between the peak flop or something multiplied by the peak bandwidth. This something is the ratio between the flop and the amount of bytes that your application needs, which is named arithmetic intensity. And it's a property of your code. So this defines, at the end of the day, 2 lines in a plot. Which one is the diagonal one, which is a peak DRAM. Here you have arithmetic intensity, you have flops, attainable flops, and the roof here, which is the peak performance. So here, a point in this plot will be your application, And if it hits this line, you are memory bound, so you are bounded by the gigabyte per second. If you hit this one, you are bounded by the peak flops. So that allows you to understand where you are with your application and the performance of your architecture. To give you a practical example, and then I will finish. So this is a plot which shows 5 months of jobs executed in the Fugaku system, plotted in its room-flying model of the E64FX. So each point here was a job from which has been measured the bandwidth and the flops it attained using performance counters. It has been put inside the room-flying model. So you can see, for instance, that if you pick up this job is run really inefficient with respect of the capacity of the system. You have many jobs here which hits the memory bounded. So these were using the entire bandwidth of your processor. And that one on the top were instead the one which were using the peak performance. So if you would have decreased the bandwidth, for instance, taking the processor that is in Cineca, this has 1 terabyte of bandwidth, the other had 300 gigabyte. So you move it here and you squeeze the performance of some of these jobs. If you add there, you have only 3 teraflops. Cineca machine had 6 teraflop performance. So you can increase and some of the top can go faster. This is a way in which you can represent where are your jobs with respect of the peak performance and peak bandwidth, and you can use it to plan what you should buy as a next system. Okay, these data are public, so you can play and have fun with that to see how they are in reality. Okay, this concludes.